Hello, my name is Derek Knowles, and I am a PhD student under Professor Grace Gow in the Stanford Nav Lab. Today I will be explaining how you can use a tool from graph theory called Euclidean distance matrices in order to both detect and exclude faulty GNSS measurements. We have an increasing number of satellites for position, navigation, and timing in orbit. As an example, the sky plot shows that in downtown Denver, in open sky conditions, you could see more than 48 satellites on a August afternoon. At the same time, as we operate in urban conditions, there are also a large number of faults, and by faults in this presentation I mean multipath, satellite faults, and so we have a desire to be able to handle faulty signals even when we're receiving many measurements across many different satellites. So we need a fault detection and exclusion algorithm that can handle this scenario with many satellite measurements and many faults. In the past, there have been a number of fault detection and exclusion methods. One of the common methods is state solution separation. So in this method, you calculate a receiver position using all satellite measurements, and then you create combinations of satellite measurements, compute the receiver state using just those combinations of measurements, and you check the consistency by how far the solution changed between those combinations. And so this method is accurate, however, it is extremely slow as you have an increasing number of measurements and number of faults, simply because you have to create all the possible combinations of measurements. So this graph shows you that, say, like in the example on the previous slide, we have 48 measurements, and we're trying to exclude half of those are faulty. We may be up in the order of magnitude of 10 to the 12 number of combinations that we have to calculate. And so there have been a number of works aimed at improving the speed of making methods that are faster. So one of those methods does a consistency check in a greedy way based off of the pseudo-range residuals. So this method calculates the difference between the pseudo-range that you would expect from a receiver's position and the satellite's position versus what measurement you actually receive. It removes the largest pseudo-range residual, the difference between those two, and then continues to remove greedily measurements until you're below some given threshold. Another method, presented actually last year here at the conference, is searching in a 4D space of the receiver state. So rather than searching in the measurement domain, you search in the receiver state domain. And so this method is fast, given that if you have a small grid, if you know your receiver's position, and you have many measurements, this method can be faster. And then a final method uses a tool from graph theory called Euclidean distance matrices. This work I presented 2 years ago uses Euclidean distance matrices in a novel way, which I'll talk a bit more about. And then over the past 2 years, we've had improvements to this EDM-based fault detection that increases its speed despite many satellites and many potential faults. So in this presentation, I'll start by giving a brief background on Euclidean distance matrices. I'll explain how we can use those matrices for fault detection and exclusion, and then I'll share some experimental validation. So first of all, 2 years ago, I presented a work on how you can apply Euclidean distance matrices to the GNSS navigation problem. So to start this off, a Euclidean distance matrix is filled with the squared distance between all point pairs. So all pairs of points in a system, we create a matrix based off the squared distance between all of those. So say in our example we have a system comprised of 4 points, a receiver, and 3 satellites. We create this matrix, and along the diagonal is the distance between any point and itself is 0. Then say the distance between the satellites and the receiver all have 3 units. Then we fill in the matrix with 3 squared. And then finally, if we know that the satellite positions, we can calculate that the units between all of the satellite positions are 1 unit. Then we can fill in 1 squared in the Euclidean distance matrix. And then I will keep it brief. If you're interested to know more about this GNSS navigation problem, I refer you to citation 7. And if you're interested in learning more about Euclidean distance matrices in general, I would recommend this paper, the citation 8. And so I'll keep it brief of just explaining the necessary math. So one of those is that you can recover a Gram matrix from a Euclidean distance matrix through double centering. So a Gram matrix is just a matrix in the form of X transpose X. And then the important thing will be that this Gram matrix, its rank equals the dimension of the state space. So we're trying to localize in a 3-dimensional XYZ grid for the receiver position, then this rank should have dimension of 3. And so the foundational thing is that if we take the eigenvalues of this Gram matrix, when there's not a fault, the Euclidean, all the distances, all the eigenvalues are close to 0 except for the first 3, showing that the Euclidean distance matrix has a rank of approximately 3. However, when we do add a fault, all of a sudden the 4th and 5th eigenvalues jump up to be extremely non-zero and continue to increase. However, this is in the noiseless case, or at least to machine precision. However, in the case where we have noise, natural noise in the system in GNSS measurements, the 4th and 5th eigenvalues are never exactly 0, but we still see a large jump between the normal noise in a system and the scenario where there is a fault, added fault in the system. And so we'll now, based off of those characteristics, now explain how you can perform fault detection and exclusion using that knowledge. So the first thing that we do for fault detection is we construct that Euclidean distance matrix using measured pseudoranges and known satellite positions. So remember, we never actually need to calculate a receiver position in order to do this. We simply can use the measured pseudoranges and then the known satellite positions in order to create this Euclidean distance matrix. We then, using the math in the previous slides, recover the Gram matrix and we calculate the eigenvalues of that Gram matrix. Then, as our fault detection test statistic, we compare the mean of the 3rd and 4th eigenvalues against a provided threshold. So this detection threshold is set manually, either manually or automatically through post-processing and it corresponds to, it will change based off of the amount of noise in your receiver measurements. So we take the mean and then we normalize by the first eigenvalue. This allows it to be relatively, to be more agnostic to the amount of noise in the system. And so for our fault exclusion strategy, we calculate the eigenvalue decomposition from the previous slide, and then we use the eigenvectors. So the intuition is that these two vectors, the 4th and 5th eigenvectors, give you some intuition into the measurements that are causing those 4th and 5th eigenvalues to be non-zero. We then sort by the largest absolute value, averaged across the 4th and 5th eigenvectors, and then we greedily remove the largest absolute value. So if you'll notice in this column, the largest values are at index 0 and then this fourth index. So that 0 index, if you remember from the previous slide, is the index of our receiver. And so the intuition here is showing that this fourth index, the measurements in this fourth index are the faulty measurements, and that's causing a large change in the receiver in that 0th index. So overall, our greedy Euclidean distance matrix fault detection and exclusion algorithm is shown here in this simple algorithm. And so actually the simplification of this algorithm is a greater advantage over our prior work from 2 years ago. And that you can directly implement this algorithm and have good performing results. So the first thing that we do in this algorithm is we check for faults using the eigenvalues, doing eigenvalue decomposition of this Graham matrix. Then we greedily exclude satellite measurements using those eigenvectors. And then we continue in this loop until our detection statistic falls below our given threshold. And so, as you can notice, there's no combinatorial search needed. We don't have to create combinations of different measurements, and we never had to calculate a receiver state. So this prevents the large time, computationally heavy problem of finding a receiver state estimate. So now I'll explain some experimental verification. For experimental verification, we used a simulated dataset from 9 locations across the world, and the goal of this dataset was to create a large number of varied satellite geometries. In some locations, we created a larger elevation mask. So Zurich is one of those, where we added a 30-degree elevation mask to decrease the total measurements. So across this dataset, the graph on the right shows you the number of satellites in view. We have a maximum of 48 satellites, so a large number of measurements, a minimum of 3, and the average is 29, which is still a large number of measurements. We added we added noise of 0 mean and standard deviation of 10 meters. And then in our results, we change the amount, the size, the magnitude of the bias from 10 to 60 meters, as well as randomly selecting 1 to 12 satellites to be biased. And so, in terms of computation, the greedy Euclidean distance matrix outperforms greedy residual, and although the asymptotically largest steps are the same for both of them, so the pseudo-inverse for the residual method of calculating the weighted least squares receiver position, as well as the eigenvalue decomposition for the EDM method, both have big O of n cubed for the number of measurements. However, in implementation we see that Euclidean distance matrix fault detection and exclusion drastically outperforms. And this may be due to the decreased load, special properties of this eigenvalue decomposition, and the fact that it is symmetric and positive semi-definite. So it's easier and quicker to calculate this eigenvalue decomposition in practice. So now in terms of accuracy, both algorithms have similar accuracy and are increasingly accurate with larger fault biases. So both algorithms, it's easier for them to pick out which measurements are faulty when those faulty measurements have larger biases. So in this plot we show the false alarm, the true positive rate, so correct detections of faults, versus the false alarm rate. And so the better an algorithm is, the closer it'll be to staying along this left side and top side of the graph. So in this graph we see also that Euclidean distance matrix, the greedy EDM method, has similar accuracy, so the that are the solid lines are the greedy EDM method, has similar accuracy to the greedy residual method in dashed. And then also like to mention that both of these implementations of greedy residual as well as greedy EDM, FDE, are open source in the GNSS libpi library, which are my lab, the nav lab, has written. It also includes tools that we use to create the simulated dataset of automatically downloading ephemeris and creating the visualizations in this presentation. And so if you're interested in learning more, I invite you to come to to listen to my Friday session C6 presentation on state estimation from the Python GNSS library. So in summary, I've explained how you can use Euclidean distance matrices in a greedy FDE algorithm in order to decrease the computation time of fault detection and exclusion in the presence of many measurements and many faults. This greedy EDM method avoids combinatorial searches. There's no need to calculate explicitly the receiver's state at any point, and it is fast in the scenario of even in the scenario of many measurements. I'd like to acknowledge the funding from both JPL and NSF, and thank you for your time.